Okay, so hopefully everybody can see the title slide. Using CryoSat-2 ice thickness to initialize the Navy's ice modeling system. I'd like to thank my co-authors. I'm on slide 2 now. So we've got the folks from NRL, Dave Hebert, Pam Posey, Alan Wallcraft. And we'll work with Sinead Farrell, and then William Johnson, Lee, who's with NRL's remote sensing in DC, Nathan Kurtz, Michael Phelps, not the swimmer, Rachel Tilling, and then Andy Rideout. So we've submitted this work to Advances in Space Research. So just an outline, I'm on slide 3. I'm going to give you an overview of the Navy's operational model, talk about how we've reinitialized it with CryoSat-2 data. We had 2 inputs from ESA derived as well as NASA. And I'll look at the model data comparisons from IceBridge, some upward-looking sonar from Woods Hole, CRREL ice mass balance buoys, and we've also looked at ice drift from the International Arctic Buoy Program, and I'll close up with summary and future plan. So I'm on slide 4 now. So this is the Navy's Arctic Cap Nowcast forecast system. It consists of 3 components. The ice model is CICE version 4. The ocean model is called HICOM for the hybrid coordinate ocean model. And then we use the Navy's data simulation system for ocean and ice observations called ENCODA. That stands for Navy Coupled Ocean Data Simulation. The modeling system is coupled through Earth System Modeling Framework, so it's two-way coupled. And we force it with atmospheric forcing from the Navy's global atmospheric model called NAVGEM. I apologize for all these acronyms. The resolution of the model is on a 1/12 degree grid, which is 3.5 kilometers at the pole. This model has been operational since September of 2013, and it's run daily at the Naval Oceanographic Office, which is co-located with us here at the Stennis Space Center. So the Arctic Cap produces a nowcast and a 7-day forecast of ice concentration, ice thickness, ice drift, and the like. And it provides ocean currents for the Northern Hemisphere. The products are pushed daily to the U.S. National Ice Center as well as NOAA. What you're looking at on the right, if you don't have the PDF online, this is just an animation of 30 days, September, October of 2016. You're looking at ice concentration. And the black line that you will see is from the NICS Independent Ice Edge, and that's what we use for our verification of the ice edge. This system will be replaced by a global system called GOFS, which stands for Global Ocean Forecast System version 3.1. So it'll include the Antarctic, the Southern Hemisphere. It should become operational certainly by the end of this calendar year and hopefully within the next couple of months. It's undergoing op test at the Naval Oceanographic Office. And there is a link on the upper right if you want to look at archived animations of model output. Okay, so I'm on slide 5. So the issues that we're addressing in this presentation, the Navy operational model typically has ice that is too thick in the Beaufort, Chukchi, and Central Arctic, as shown by previous comparisons that we've performed looking at CRREL ice mass balance buoy, as well as the upward-looking sonar data that Woods Hole makes available on their webpage. And I believe that data goes back to, I want to say, early 2000s. So it's a great resource, as well as the CRREL data, historical as well as real time. So with the availability of remotely sensed ice thickness data, we're investigating techniques to reinitialize our sea ice model, CICE, and develop applications to simulate swath ice thickness or freeboard. Andrew Roberts is promoting the use of freeboard into the models now in near real time for operational sea ice forecasting. So I'm on slide 6, and this just shows you a snapshot of the Arctic Cap model ice thickness reinitialized with CryoSat-2. So on the left, upper left, labeled A, that's the operational model. And you can see thick ice along the Canadian archipelago. That's not necessarily not correct, but we've noticed over the years that we tend to be too thick overall. B in the center That's the ice thickness field using the CryoSat-2 data provided by Nathan Kurtz at NASA. And then C shows you the CryoSat-2 data from ESA, and Rachel Tilling and Andy Rideout were the sources of that data. So we performed twin experiments, hindcasts, where we replaced the ice thickness field in Arctic cap with the NASA-derived CryoSat-2 ice thickness, and they use what's called a waveform fitting technique. And then C, the ESA ice thickness, and they use what's called waveform tracking. Both of these approaches make some assumption about the snow cover on top of the ice, and it's tied to climatology. So we're going to compare against Arctic cap. The simulation period is 18 months from mid-March of 14 to the end of September of 2015. The NAVGEM, our atmospheric forcing, is consistent for all three of these runs. So the atmosphere is not coupled to the ice or ocean model, and we're using the same data simulation. So what I'm going to walk you through now is some slides that just show you how the model performs. But before I do that, I do have one more slide, and this was provided by Sinead. So this is showing you an overlay of the NASA Operation IceBridge from March and April of 2014 over a composite ice thickness from the CryoSat-2 product from ESA. And if you can see, I don't know how well you can see it from the screen, but there's excellent agreement between the two independent measures of Arctic ice thickness, and a gradient from older, thicker ice north of Greenland and the Canadian Arctic archipelago to thinner ice in the first-year regions of the Beaufort, Chukchi, East Siberian, Laptev, Kara, and Barents Seas are clearly seen. Okay, now I'm on slide 8, and this is just showing you a model data comparison. On the upper left, that's Arctic cap versus IceBridge. In the middle, that's the ESA product, and on the far right, that's a NASA product. And we're comparing against 8 transects from the NASA IceBridge data from 2014, and it's going to be hard for anyone to read those dates, but they run from March 17th through April 3rd, and they're color-coded by the day that those flights were flown. So the take-home point on the table on the lower right, the mean IceBridge thickness is 2.57 meters. Arctic cap is about 75 centimeters thicker at 3.23, and you can see a much better agreement with both the NASA and the ESA products. And so the biases are much lower using the initialized data, and we see lower root mean square error as well as a higher correlation. So this is just to show you how we're starting off the initialization of our models. Okay, slide 9. So I'm going to show you the data that we're going to be doing our model data comparisons. So the black stars show you the locations of the Woods Hole upward looking sonar, and those are fixed moorings, so they do not move with time. And then the colored lines, there's a black, a blue, and a red. Those represent the CRREL ice mass balance buoys, which do drift in the ice. And so the starting position is shown in green, and the ending location is in red square. So essentially, the ice is drifting toward the northwest, except for the black, where it's a little more north-northwest. And so I'll show you next on slide 10 how we compare. So the plots on the left show you model data comparisons of the model hindcast experiments versus observation. So observations are shown in black. If you see my cursor, so this is what's being observed by the upward looking sonar, and that's a draft. So we've made daily averages of the ice draft, and we've converted that to ice thickness. The red line represents the simulated, hindcast ice thickness from Arctic cap initialized with the NASA product, and that's in red. And the green line shows you the ESA product. And so we just initialized at the very beginning, and the model runs and does its thing. So over time, we certainly would expect the solution to start to differ from observation. So this is mooring A, mooring B, and mooring D. And the table on the right shows you summary statistics by season. So the first quartile shown here on the top, this is April 1st to June 30th of 2014, and we're going to call that the spring season. So the ULS average, and this is for all three stations, averaged is a little over 2 meters. Arctic cap, we're about 1.5 meters thicker, which we know is not correct. It's 3.5. And then the NASA and ESA are significantly closer to ULS. And I've highlighted in green on this table which was the best performer. So we've got significantly lower biases, lower root mean square errors, and then it's by season. So the summer season, which we're calling July 1st to the end of September, again, you can see the ULS average is a little over 1 meter. Arctic cap is 2.58, whereas in this case, the NASA nails it 1.02. ESA is a little higher, but the take-home point is you can see consistently lower biases, mean square errors, and for the most part, we have a higher correlation coefficient. And that continues into the fall season, October through December. And then the last that I show you is from January 1st to March 31st. So this is almost a year into the simulation. And you can still see an improved ice thickness, but it's starting, the thicknesses are getting higher and moving away from what we're seeing from observation. So this is the upward looking sonar depiction. And then I do want to highlight this red oval, which I've indicated from mooring A. And so let me explain a little bit more. If you look closely, we do see a jump up in ice thickness for all three. For the Arctic cap simulation, it goes from certainly about, I'd say 1/2 meter, and it rapidly ramps up to over 2 meters, not quite as pronounced with NASA and ESA, but still significant. And we're attributing that, I'm now on slide 11, to advection of thicker ice. So here's location A, and this is on the 1st of October. Those are the other moorings B and D. But at A on October 1st, it's relatively thin ice. But by the end of the month, 30 days later, we can see thicker ice has now been advected into the area. So remember, all the models, all these simulations, all three of them are using the same atmospheric forcing. So it's helping to advect thicker ice into the region. Okay, number 12, slide 12. Now we're going to look at 3 CRREL ice mass balance buoy. And they show a similar picture. The one on the upper left, this is 2013 F, and this has the longest record. It goes from mid-March, is where we're picking up, through end of June of 2015. So again, the black line is observation. The red is NASA. Green is ESA, and I know green is a little bit hard to see, and then in blue is our Arctic cap, which I think it's quite clear it's been too thick. And so you can see very, very good agreement for either CS2 initializations through, I'd say, through late October, and then you start seeing the solution diverge. We're starting to get thicker. For the middle panel, again, a very good agreement through the end of July, and then it looks like it melts out, or at least the buoy stops reporting. I wouldn't say it melts out. And then the bottom one shows you 2014 C. Again, very, very good agreement. Look at this red line, how we initialized March 14th, and through the end of June, the two are pretty much identical. And then the NASA initialization, actually it melts out a little more than what's observed. But overall, they do well. So summary stats, the mean ice thickness is shown here in this column for the period now. This is just for the length of the record that we're showing. Here's Arctic cap. In this case, NASA is the best performer, but you can see lower biases, lower root mean square errors. Correlations are comparable. The ESA actually have the highest for this particular ice mass balance buoys, but it's a similar, I think, message for 2013 B and 2014 C. So just all we're doing is initialize the model on one day, and we see a pretty big bang for our buck. Okay, now slide 13. The last thing that we looked at was how did the ice drifts compare? Since we have maybe more realistic ice thickness, it's thinner. If we're applying the same wind on that ice, we would expect the ice drifts to pick up. We look at the Pan-Arctic ice thickness, ice drift, and I don't show that here. We really didn't see any improvement, which was a little disappointing. But when we did look at the Bering-Chukchi Beaufort Sea, and that is this area on the left in red. So if you can see that red, kind of a triangle, that's the area where we're doing the study for the Beaufort-Chukchi Bering Sea. And we used 288 of these International Arctic Buoy Program drifters. And that's how we do our ice drift stats typically for our model. And so this table shows you by month, starting June through November, number of OBS available, the observed magnitude based on those OBS, and it's on the ballpark of about 11 to 13, 14 centimeters per second. Here's our Arctic cap drift, and these are the drifts from either the NASA or the ESA initialized, and the green again shows you the best performer. So in some cases it's NASA, in some cases there's a tie with ESA. But for either one of those, we see an improvement between, I'll say 24 to 29% in ice drift during the first season. When we looked at the seasonal stats for the following year, yeah, the scale pretty much had dropped off. Okay, so I'm on my last slide, essentially, slide 14. So this is the summary slide. So we've found significant improvement in ice thickness scale on multi-year ice when the model was initialized with CryoSat-2 based ice thickness fields. And we've compared against upward looking sonar ice draft and CRREL ice mass balance buoy data. Little change for Pan-Arctic region when comparing against the International Arctic Buoy Program ice drift, but we did see a significant improvement during the summer-fall period of 2014 in the Beaufort-Chukchi Bering Seas. This is the U.S. Navy's first attempt to run a sea ice forecast system initialized with remotely sensed ice thickness data. It suggests that it shows much promise for operational sea ice modeling in the future as new sensor data becomes available. There's IceSat-2 with the plan 2018. There's other sources as well. So our future efforts will test the assimilation of swath ice thickness data directly into model. We're doing that presently with the ESA CryoSat-2 data. We're looking at the, I believe, the 8-day swath data. We want to study the impact of a blended CryoSat-2 swath ice thickness field, because CryoSat-2, it really starts at a ½ meter. So the swath data will give us the opportunity to look at thinner ice. We want to test reinitializing the model also during the fall period. Obviously during the summer, we don't have data available. And we want to look into we also participate in the Sea Ice Outlook, which I'm sure much of this group is aware of. But we're going to look into initializing our Sea Ice Outlook ensembles for the May 1st period with the CryoSat-2 ice thickness. And lastly, I guess I mentioned perform testing with IceSat-2. One of the issues with IceSat-2 is the latency. So, you know, it's going to be anywhere from, I'd say, 30 to 90 days. So we have to develop a appropriate technique to make use of that data effectively. And that's my last slides. And then I did have one slide if people wanted to ask any questions, or Meredith, did you want to wait to the end? However.
Jackie, that's up to you. We do have a question in the chat box.
Yes, I'd like to go ahead and have people ask questions now, and then we can, you know, I'll keep track of the time and before we move on to Alex's talk.
Okay, so if anyone has questions, they can unmute themselves. I had to mute a couple people, so you will probably need to unmute yourself, or you can type your question in the chat box. And we do have a question from Igor, and he asks if thin ice in leads is included in model and the CS2 data.
Yeah, so what we did, we just used CryoSat-2, so we didn't have any thin ice, so the cutoff is about a ½ meter. So I believe we used some type of interpolation techniques, or if it was a ½ meter or less, we set the ice thickness to, I believe, a ½ meter. And then the model will make an adjustment based on what the ocean temperature is. So if we tell it there's ice there, then the ocean will lower the water temperature, surface temperature to freezing point. I don't know if I quite answered your question or not.
Yes, I understand it. Thank you.
Okay, thank you.
Rick, this is Jackie. I really appreciate the presentation. The work is extremely exciting and very promising. Can you give us some insights on what you attribute the impact of, you know, using these data to initialize the model, why that's showing such good improvement?
Well, I would just say, and we didn't cherry pick, so it's not like we ran a whole bunch of experiments and said, oh, March is the way to go. You know, we looked at, do we want to initialize in February, March, April? We weren't quite comfortable to go into May. So we thought if we had an experiment where we started mid-March, you know, the plan was to run it out for at least 2 summer seasons. Now, we were honestly surprised at the skill with time. You know, if you recall some of those tables and even the time series, they do show, in my opinion, scale out to 6 months, which is pretty surprising. And then the fact that we've known for quite some time that our model is too thick, the fact that this product seemingly as robust as it is, you know, that's really encouraging. And then our plan is to augment that with an assimilation of near real-time data, you know, the swath type data from whatever source. I believe there's Sentinel-3 is another source, you know, of potential ice thickness data. So yeah, I don't know, am I answering your question or, yeah, we were pleasantly surprised.
Yeah, I guess I was just kind of, I was interested in getting a sense of what you thought that information was really doing for you. You'd think it's just kind of that starting point, getting a good starting point into the season?
Yeah, I think it's just a great initialization, you know, for, in this case, you could call it, you know, at almost the maximum extent, you know, of your ice. And one thing that I didn't show, we looked at one Central Arctic ice mass balance buoy. I don't remember the number, but it started probably 6 or more months before our simulation period. And the interesting thing was our model, our Arctic cap, as well as the NASA and the ESA product, they all were pretty similar. And I guess what that was telling me at that point in time was this CryoSat-2, I guess I could say that our model in the Central Arctic in March of 14 was actually doing pretty well. And then when we reinitialized, it wasn't that much different, you know, than what the model had thought the thickness should have been, so.
Do you think that explains also the reason why when you compared the Pan-Arctic drift that you didn't see that much change?
I think that's part of it. You know, we were surprised. I expected something better than nothing, and it was pretty much zero-sum game for the whole Pan-Arctic. We also saw some improvement for the Greenland, or what we call the Greenland Norwegian Sea area. But since there's a lot of interest, obviously, in the Beaufort Sea bearing, you know, if we're going to do best in an area, certainly that was pleasantly good to see.
Cool. Meredith, do you have any other questions? Because I have one more. I don't want to.
I have one question. Hi, this is Guillermo from BOM. Nice presentation, Rick. Thank you. What are the next steps in terms of resolving the discrepancies that you showed at different points in time? Do you have did you identify possible causes for those discrepancies, or it's all embedded in the overall system?
Are you talking about discrepancies at the initialization period or as the model hindcast ran, over the course of several months?
In the hindcast part.
Yeah, I mean, I think in initialization, I think we're from the data we're looking at, and most of the data is unfortunately just in the Beaufort Sea Bering Sea. I have tried to get other upward-looking sonar data off the coast of Greenland, and if anybody knows anybody out there that's willing to share more real-time data, we would love to look at it. But with the data that we have access to, we're pretty pleased with the product. I don't want to, at this point, say which is a superior product. I think both the ESA and the NASA product, do show a lot of promise. And from a Navy perspective, we'll have to dig a little deeper to determine, which is the most appropriate, or if there are a better way forward as well.
Yeah, and another way to phrase my question is, what's behind the too thick sea ice in your model?
Oh, in the operational model.
Yes.
Yeah, well, we spun that model up from equilibrium many years ago, and certainly some of it could easily be just the atmospheric forcing we use to drive the model. We've had upgrades to that model over the last several years. We're also developing a global system, is what's called ESPC, the Earth System Prediction Capability. So that's a global air, ice, ocean, and then eventually wave fully coupled system. So we're just starting to test that right now. So it's a little premature for me to speculate on how that will perform, but certainly like for our sea ice outlook, that's what we're using, this ESPC system. So I think coupling directly to the atmosphere could potentially show some improvement as well.
Thank you.
Sure.
Jackie, there are a couple of questions in the chat box if you want to get them answered.
Go right ahead.
Okay, so, and I apologize if I get the pronouncing the acronym wrong, but one question from Bits, not sure who that is yet, but CISA 4 has an ice edge thickness distribution, thickness categories. How did you distribute the CS2 data into these categories? Did you put them into a single category maybe?
Yeah, we use five ice categories, and so we essentially rebin the data so it's stable within the model, and there's a routine in the CICE model that does that. So that's how that was addressed.
Okay, and there's one more question. Is accuracy of the ice edge location forecast improved as well? I don't
think I can answer that. We did not look at that. I know that we've been making improvements, certainly in the ice concentration. More recently, we've added the IMS, which was a joint partnership with NASA, the National Ice Center, and then the Snow and Ice Data Center with Florence Federer and her group. And we used a 4-kilometer product, so we've shown improved scale. We're actually assimilating that now in the model, but Pam Posey has been adding the VIIRS ice concentration to the mix, and VIIRS is much higher resolution. It's on the order of maybe 500 meters. The model, of course, is not at that resolution. But for the 1-year period of 2016, she has found a 25% improvement in ice edge area when we just add VIIRS to existing AMSR2, SSMIS, and IMS. So we're doing well on the ice concentration, but we have a ways to go, obviously, on the ice thickness, and we want to make some inroads on that.
Okay, that looks like it, right, Meredith? That's all I see.
That's correct.
Any last questions before we move on? Just before we leave, again, Rick, thanks so much for your presentation. I also want to note I'm thrilled to see you using the in situ data as well to evaluate the model. Getting to see the model with satellite data and in situ observations is such a cool intersection, and it's good to see the effective use of them.
Yeah, no, we enjoy it. We appreciate all the work that others have done over the years, making that data available, and to actually start to be able to use it in a meaningful way is a positive.